that is digital transmission of analog signals. Digital transmission of analog signals. So all the natural signals are mostly analog. So we would see how we'll transmit this analog signal in digital format. Uh, so why do we generally transmit analog signals to digital in digital format? Because digital communication offers several important advantages. So communications digital communications offer several important advantages compared to analog communications. Compared to analog communications, digital communication offers several important advantages. And if we name a few, higher performance. If we name a few of the advantages, the first one of the advantages, higher performance. Higher performance. Second is greater versatility and higher security. Versatility means this is immune to noise, more immune to noise. And it is also offer higher security and higher security. So digital transmission of analog signals, we do it. What is the motivation for this? Because digital communications offer several important advantages compared to analog communications. For example, higher performance, more versatile and higher security. So you have to first convert your analog signal to digital format. Digital signal. So you have to do analog to digital conversion, right? So the device which is used to do, which is perform analog to digital conversion, is called analog to digital converter device. So this process of converting your analog signal to digital signal is referred as digital pulse modulation. So this process is referred as digital pulse modulation. So what we are doing here, we are converting our analog signal to digital signal in order to send it to a digital format, and this process is referred as digital pulse modulation. And the two important techniques which we use is pulse coded modulation, pulse code modulation, that is PCM. We also abbreviate P for pulse, C for code, M for modulation, and delta modulation, also known as DM, delta modulation. And the abbreviation we use for this is DM. So the process of converting your analog signal into digital format is also referred as digital pulse modulation. And the two important processes that we use for such a conversion is pulse code modulation and delta modulation. So let's start first with the pulse code modulation, and subsequently we will read delta modulations. So the next topic is pulse code modulation. All these recordings will be available to you. So if you want to make the notes, it is okay. If you don't want to make notes and you want to make notes later and try to focus and here, so that is also okay with me. And if you want to go slow, let me know. So what we have studied, we have seen that digital transmission of signals offer few advantages such as higher performance, higher security, and that is why we generally transmit analog signal to digital signal. And the process which we use in order to convert your analog signals to digital signals is called digital pulse modulations. And the two more, I mean, generally used two important techniques of this A to D conversion is pulse code modulation and delta modulation. So first we start with the pulse code modulation. So the PCM consists of following steps. First is sampling, second is quantizing, and the third is encoding. So under this pulse code modulation, we first sample your signal, analog signal. We quantize these sampled signals or we quantize the various levels and then we provide some bits to each quantized level. That is called encoding. So we'll see. So we can also plot it. Sorry, not plot. We can draw a diagram. But that first be a sample. This is your sampler diagram, sampler block diagram, sampler block, followed by the output of the sampler is fed to your quantizer. And then each quantized level is provided some bits, and that is called encoding. So MT is your analog signal. Passes through sampler, then quantizer, then encoding is done. So what is the definition? Let's write. Let's reiterate. I would reiterate this the definition of this sampling. So the definition is the process. Sampling is the process. Sampling is the process in which a continuous time signal it is sampled by measuring its amplitude at discrete instants, at discrete time instants or the space instants. We are generalizing here, right? See if you are having a, for example, a two-dimensional picture, so that is an analog. If you remember the old cameras which we used to which we used for the to capture photographs, negative wala, if you remember that negative um, old photographs, so in which we get the photographs that is in analog form, right? But they are in two dimension, right? So we can sample it. If we sample, we take many points in this xy domain, in this xy space. So we will sample at space. That is why I'm not specifying a time. So the process in which a continuous time signal, or this time is rather, you can understand it like it can be a space also, to sampled by measuring its amplitude at discrete instants. Though I am using time here, but it can be space. So the process in which a continuous time signal is sampled by measuring its amplitude at discrete instants. So this is called sampling. By the very name of this sampling, you can understand, like you are taking the samples at different instants. So this is not very difficult. Now you represent these sampled values of the, now you have what? You have sampled values, you have sampled amplitudes, right? So representing the sampled values of the amplitude by finite set of levels is called quantizing. So representing the sampled values of the amplitude by a finite set of levels is called quantizing. So what is quantizing? Quantizing is you have sampled values of amplitude, and then you represent these amplitude by a finite set of levels. So we will elaborate on each of these definitions. So just for the sake of completeness, first I would like to state those definitions, and then we will further elaborate on that. So then designating each quantized level by a code is called encoding. So now we have the formal definitions of sampling, quantizing, and encoding, that are the three parts of the pulse code modulation process that is used to convert your analog signals to digital signals. Correct? So we have formal definitions first. So what is happening when we apply sampling? Your continuous signal empty would give you discrete signal. Correct? This is your discrete time signal will become a discrete time signal because now you are sampling at different instants, right? Different time instants. If you are sampling your input signal, it will give you a discrete signal because it's no more continuous. You can think it like you have chopped your continuous wave in various in different times. Now you have only the chopped values. You don't have all the continuous values. So this is the discrete time signal. Then you provide you have various sample, right? Various samples. Then you provide. Then you do not take all the samples, right? Um, Let me try to explain it to you in a more. So see, these MNT can take many values. So if I draw a continuous signal like this, you sample it at different time instant. So you have a this, this, this. For example, 5. These 6 samples. Now you will not. These 6 samples can take any values, right? If you have a signal which is like taking value from Vmin to Vmax, if you are considering a voltage signal, if you are having a voltage signal and it can take value from Vmin to Vmax, then your MNT or the samples can take any values, though they are finite, but they can take any values. But after the quantizer, once you pass all those samples through quantizer, it will not be having any value possible. You will provide discrete amplitude. See, now your amplitude is not discrete, it can take any value, so it is continuous. But now you will discretize your amplitude axis also. It means you can, if your sample lie within a range, then you will give a particular, you will assign a particular label to it. Okay, so it is a discrete amplitude. Now you convert your discrete in amplitude. After the quantizer, so I write it m hat. We use as m hat as a it's just notation. So we use m, and mnt was your sampled version, and m hat nt is your discrete amplitude sample and time, and discrete in time, both, right? So it is discrete in time and discrete in amplitude. Now you provide each sample some values, some code. Okay, so let's. So the quantizing and encoding operation are usually performed in the same circuit, which is called A to D converter. So I wrongly told you that this whole process is called analog to digital converter, but the device which perform this quantization, if I use a red pen for that, this is a quantizer and this is encoding. So these two operations are performed by analog to digital converter. Analog to digital converter. ठीक है? So we will discuss each thing, each operation, that is sampling, quantizing and encoding. ठीक? Or you should write encoder here, not encoding. So we'll first start with the sampling theorem. Sampling theorem. So before going to the sampling theorem, we will say what is your band limited signals. What is the band limited signals? So if mt is a time domain signal and its Fourier transform is mf, then it is non-zero mf, or you can say mf is 0 for mod of f greater than f. It means your mt is something like that, minus fm to fm. It is non-zero in this range and 0 outside this range. So this is your band limited signal. Okay. So what is the definition of a band limited signal? The frequency, the Fourier transform, the Fourier transform of a band limited signal is zero above a certain frequency, above a certain frequency. ठीक है? So this is your band limited signal. Now let us write sampling theorem. So if your MT is a real valued band limited signal, if MT is a real valued band limited signal, then MT can be uniquely determined from its values M and Ts, sampled at uniform intervals Ts. The interval, the Ts, should be less than 1 upon 2 Fm. And this Ts is your sampling period. This Ts, if MT is a real valued band limited signal, then MT can be uniquely determined from its value M and Ts sampled at uniformly interval Ts, and you can write M and Ts sine 2 pi Fm T minus NTS divided by 2 pi Fm T minus NTS. This is your MT. In fact, MT is given by this equation. So sampling theorem states if MT is a real valued band limited signal, then MT can be uniquely determined from its value M and Ts sampled at uniform intervals with this Ts is your Ts is Ts we refer to Ts as the sampling period and to its reciprocal 1 upon Ts as the sampling rate. So if Ts is less than or equal to 2 Fm, then your sampling rate Fs, if Ts is 1 upon 2 Fm, this implies 1 upon Fs is less than 1 upon 2 Fm, and this implies that Fs is greater than 2 Fm. Your sampling rate must be twice the maximum frequency component of that signal MT, of that band limited signal MT. So we can also, in other words, we can write the sampling theorem states the sampling theorem states that a band limited signal, a band limited signal which has no frequency component higher than Fm Hertz can be recovered completely from a set of sample taken at the rate of fs samples per second. So the sampling theorem states that a band-limited signal which has no frequency components higher than FM Hz can be recovered completely from a set of samples taken at the rate of Fs samples per second. So this is the statement. So this sampling theorem, I would say remark. So just note that that the, this sampling theorem is often called the uniform sampling theorem for baseband or low pass signals. So though it is a band limited, but it is baseband signal. So this sampling theorem is often called the uniform sampling theorem for baseband or low pass signals. Though it is band limited, okay, so that is assumed. And what is the minimum sampling rate? I have told you that the rate should be greater than equal to 2f. So what is the minimum sampling rate? The minimum sampling rate is 2fm. This minimum sampling rate is 2fm samples per second. This is also called Nyquist rate. This is called Nyquist rate. Nyquist rate. And its reciprocal is called 1 upon Nyquist rate is Nyquist interval. Now let's see the proof of this sampling theorem. So let's go to the proof of sampling theorem. So why do we need this theorem? The question is this: why do we need these theorems? See, we have already seen that in order to convert your analog signals to digital signal, you have to first sample them, then you quantize them, and then you encode them. So sampling must be done in such a way that we don't lose information, that we should be able to perfectly reconstruct your analog signal by using those samples. So Nyquist says, or the sampling theorem says, if we uniformly sample our band limited baseband signal with a rate that is greater than 2 FM, then we can perfectly reconstruct the analog signal. We don't lose anything. So this is the sampling theorem statement. So that is why we need this theorem. Otherwise, we would lose the information, right? So let's prove it. Let I like this word let. In all the proofs, we start with let, right? Let MT be a band limited signal defined defined by so this is your MT, and its Fourier transform is like this. So this is your band limited signal. And the definition of band limited signal we have seen, right? This is the definition. The Fourier transform of a band limited signal is zero above a certain frequency. So now we sample this signal, this empty signal with some rate, some time ts. So sampling this is nothing but multiplying this with a impulse train. We multiply this uh, empty with the impulse train, and the impulse train, that period is ts. So we multiply this empty with this impulse train, and we represent impulse trains with delta tst. Ts is the interval of this impulse train, and delta is a, because it's an impulse train, right? It's not a train. I mean, it's a set of many impulses in a regular interval. So it looks like train, impulse train. Okay, great. Jokes apart. So this is your impulse train, and and one important characteristic of impulse train is that its Fourier transform is also impulse train. So the Fourier transform of impulse train is also a impulse train. So this is a impulse train. Okay, we here in this book we are using the omega, so we will stick with that notation. And it is 2 pi by ts 0 and 2 pi by ts. This is your now. If you want to sample this empty with a regular, with the interval ts, we have to multiply this impulse train with this empty. So let's multiply. Sorry, yeah, we multiply this and we will get a something like this. This is your so this is your empty, and you sample it. sample it, right? 0 ts, 2 ts, and so on, minus ts, and so on. And the, then we take its Fourier transform. And the Fourier transform of this, when we multiply your impulse train with your signal mt, the Fourier transform is repetition of your m omega with at interval that is omega s. So this is your multiplication, the Fourier transform of multiplication of mt with the impulse train. So this is your Fourier transform of m. We represent it with ms omega, and this with ms t. This is a sample t, right? So, or you can also write mnt, but it's okay. It's not. So this is the third step. First step is we plot mt and m omega. We plot the impulse train and its corresponding, its associated or its corresponding frequency Fourier transform. We plot we multiply the impulse train with mt and we see how its Fourier transform looks like. Yes, so up to this point, I hope everything is clear to you. So if you see that if we increase this ts, see here the ts is such that your omega s is your omega s is greater than 2 omega m. But if you choose, so it implies that 1 upon 2 pi by ts is greater than 2 into 2 pi by what was the time duration of this 2 pi fm 2 pi fm. So ts was less than equal to 1 upon 2 fm. But what if you increase your ts more than this value? It means you multiply your input signal with the impulse train of interval less than this 1 upon 2 fm. So if we increase your ts a bit more, this is your new tss, and you multiply your message signal with this impulse train so this type of samples you will have. And the Fourier is, as I told you, the Fourier is actually Fourier is the name of a scientist who discovered this Fourier transform. So 0 omega s, this is 2 pi by ts, which is, and similarly you can put values, right? So its Fourier transform will give you the overlapped version of the frequency response of this m omega. This is your pulse. So now you can see that there is an overlap. So we are losing, I mean, since there is an overlap, we have lost the whole frequency component of your signal empty. So if you want to reconstruct it, if you pass it through a filter, then we will not be able to completely recover your empty because we have lost some part of its spectrum, right? Which is quite visible from your from this figure. This is your 2 pi fm. This is 2 pi by ts, and since your ts is chosen in such a way that it is more than 2f 1 upon 2 fm, it is creating such problem. So now we know that your ts should be less than equal to 2 fm, or your fs should be greater than equal to 2 fm in order to have a perfect replica of your frequency spectrum. So this pictorially we have seen that, and mathematically next we will see we will mathematically see this and try to prove. It's a little involved. This pictorial view is a little easier to understand and it is more appreciable. That is why I have started with the pictorial way of proving this. So we will discuss it in the next class.